Okay, so what are we going to examine this week? So this week, we're going to talk about a lot more in depth about the random forest model. We're going to consider why using the forest is better than using a single tree. We're going to ask ourselves how the forest is actually set up. Okay, how do we construct the forest from these individual decision trees? And finally, we're going to begin examining this question of how do we understand the output of the random forest? How do we use it to explain a certain situation? Okay, this problem of explanation is going to be something that comes up again and again when dealing with these machine learning models. We're going to look at some different measures of variable importance, and then we're going to look at how to compute the partial effects of the model. Okay. Um, Maybe some of those things seem a little bit cryptic at this point. Okay, but we'll get to them. Okay. But let's begin by considering the problem of, or considering the question of why the random forests are necessary at all. Um, the decision trees that we've been building, these decision trees, they already seem pretty useful, right? So, but in a random forest model, we often are going to be building hundreds, if not thousands, of these trees. So, what's the point of doing that when even the decision trees look like they could make some pretty decent predictions? Well, so as it turns out, these decision trees, they have a bit of a problem. They're very inconsistent. Okay. Basically, you could change your data only a little bit, and then you would end up growing a very different tree. We're going to demonstrate this. Okay. And well, that's not very good, right? Because, imagine, imagine you're going to weather.com and looking up the weather report. Okay. And you go and you want to know what the weather is going to be like tomorrow. And it says tomorrow the weather is going to be sunny and 70 degrees. You're like, okay, great. And then now imagine you hit the refresh button on your browser. You refresh weather.com, and all of a sudden tomorrow it's predicting rain. And you click it again. All of a sudden it's predicting sun again. You refresh it again. All of a sudden it's predicting like a hurricane. Well, that wouldn't really be a very useful weather forecast, right? And the decision trees, you'll see they sort of have this problem. Now, that seems like a bad thing, okay? But what you'll see is that the random forest algorithm can actually, in a way, exploit this inconsistency to yield much better predictions as compared to a single tree. Okay, so let me demonstrate this for you, and this is we're gonna go into the code. Okay, let's go over here. Um, hmm. Okay, let's go over here. Okay, so to begin with, I'm just gonna start by loading up all the packages that I'm gonna use. Let me actually do a couple of things. I'm gonna move my image over here. I'm gonna see if I can make this a little bit bigger for y'all. Let's see if I can increase the text size a little bit here. Okay, hopefully y'all can see that. Obviously, you have this on your own computer as well because you have this file, okay? So just try to follow along. So the first thing that we're going to do is we're going to simply load up a bunch of packages. We're starting to use a lot of packages now. All right? So we might as well load them up all at the beginning. So let me load all of these packages. And if you find that any of these packages don't run, you just want to run that install.packages command, okay, to install the package. Okay, so then we're going to load up the Titanic data set and do the data prep just like we've been doing. Okay. And finally, we're going to split the data into training and test sets. All of this code is we're just reusing the code that we had from last time. Okay. let me actually make this even a little bit bigger because I have some extra space. Go to 18. Okay. So now you'll note, okay, that these 4 lines that we've been using to create the training and the test set, usually we start off by running this set seed line, okay? And I've actually disabled this line in our current version of the code. Notice I've simply turned it into a comment. This is called commenting out a line of code. That disables that, okay? Now what does this set seed line do? Well, you see, if we set the random seed, okay, every time we make this split into the training and the test set, it's going to be consistent. Okay. So in other words, so how does the computer, determine what data goes into the test set and what data goes into the training set? Well, it just does that randomly. Okay. Um, and if you set the seed to a specific value, even though it's doing it randomly, you'll get the same results every time. If I disable that command, you'll see that basically the computer will select different data points to go into the training and test set each time. Okay, so let me show you that. So I'm going to just run these 3 lines here again. Okay, and then I'll show you the Titanic data set. So here's the Titanic data set. So you can see, Miss Elizabeth Walton Allen split is equal to true. So that means that that person will be in the training set. Okay, this next person, they'll be in the test set. This person, training set, test set, test set, test set. Okay, so that's sort of the pattern. But if I were to run this again, just run those exact same lines of code again, what you'll see is that it's a different pattern here. Okay, different people are going to be in the test set versus the training set. Okay, so that's what that does. Okay, and what I basically want to see is I want to see whether this process of having a different group of people being selected to go into the training set, whether that affects the outcome of our estimation. Okay. And first I want to show you what happens when we do this with a regular old OLS regression, the kind of model we were dealing with earlier in the semester. Okay. So I'm going to run this code. I'm going to train an OLS model. I'm going to, target the training set. I'm going to, use the training set to train an OLS model. And then I'll simply display the output of the model by saying summary OLS. Okay. So let me do this once. Okay. And you can see, okay, so here are our estimates. So the coefficient is 0.42 on gender, okay, minus 0.007 on age. Okay, so you can see what those values are. Now, what I want you to do is select that code and simply run it again. Okay, and run it again. Just keep running it. And what you'll see is that the numbers change every single time. They change slightly because we're including a different set of people in the training set and therefore giving the algorithm a different initial set of data to look at. Now, here's the thing though. What you'll find is that as you sort of run this over and over again, these estimates, they don't really change by that much, right? Like, for example, this coefficient on gender, it's kind of going up and down. Maybe sometimes it's 45, maybe sometimes it's 52, but it's still around that 50 range. It's not really changing all that much. Okay, so what that means is that, this model, the OLS model, it's a pretty consistent estimator. It's fairly robust to these types of, changes in the training data. Okay, so now what I'm going to do, okay, is I'm going to do that exact same thing. So I've literally copy pasted those 3 lines of code to redraw our training set, essentially. And I'm instead of fitting a OLS, I'm fitting a decision tree. Now recall that the command to do that instead of LM for linear model is rpart. Okay, so that stands for R partition tree. Okay, that's another name for these decision trees is a partition tree. And notice I have the same formula as before. Okay, I'm targeting the training data just like before. And right now we're using this tree in classification mode because our dependent variable is a categorical variable, survival or not. Okay, that's just a dummy variable. And so I selected method equals class for classification. Okay, so I'm simply going to fit the model, and then I'm going to call this rpart.plot function to give us a visual representation of the tree. Okay, so let me do that. So I'm going to run that, and here we see our tree. Okay, here's our tree. Now, let me run that again. Well, okay, well that looks like a different tree, quite a different tree. You'll see that, before in that tree that we built last time, right, the first split was on gender, and that's still the case. But then the next split was passenger class for both branches. But you can see now over here, instead of splitting by passenger class, we immediately split by age. And then over here, we split by passenger class. And then there's a much more complicated set of branches over here, right? Compare this picture to the one in the slides, okay? Okay, let me do it again, okay? I'm simply going to redraw the training set and then fit a new model. Okay, it's different still. This is just like a really simple tree. For whatever reason, this tree is nowhere near as complicated as the first one. And so I'm just going to do this a couple of times, and you'll see that every single time we redraw this model, and I encourage you to do it on your own computer as well, we get a totally different looking tree. Okay, so that's what I mean by these decision trees being kind of inconsistent, right? It's kind of like that brokenweather.com website I was telling you before. Obviously, if I have a totally different tree, it's gonna make a totally different prediction, right? So, okay. So the point being here is that, once people started using these decision trees, they realized, hey, this is kind of a problem. Okay, it seems really good. It seems really useful. Okay, I mean, it can understand these contingent relationships in the data. It's nonlinear. Okay, all that's really cool, but they're very inconsistent. So then the question became, well, okay, is there a way to harness the power of these decision trees, but still have a consistent estimator, still have an estimator that pretty much gives us the same thing every time that we run it, okay? And one approach to doing that, and one of the most popular approaches, okay, is this idea of, well, let's just build then a whole bunch of different trees, and then we'll use the average of their predictions. That's essentially what the random forest model is, okay? So we'll look at that in the next video.